I'm going to prove that this function is continuous on this particular subset of its domain. And to do that, there's a process that we must follow, which I've included here in this gray box for you to see. So, as per this sort of recipe, I'm going to start by choosing an arbitrary point in this subset S. And the reason that I do this is because proving that a function is continuous on a subset is equivalent to showing that the function is continuous at any arbitrary point in that subset. Okay, so the next thing I have to do is to choose epsilon bigger than 0, and with this choice of epsilon there exists some delta, right? So we're going to let delta equal to something, which I'm going to come back to later and fill in. And as you know, the whole meat and potatoes of this type of proof is finding this delta that works. Okay, so now the next step is to choose your x, and then make your key assumption that x and x naught are at most delta apart. Well, okay, so to begin, I first of all need to compute this difference, f of x minus f of x naught. Sorry. And if you do this, you're going to get that this is exactly x minus x naught over the product x and x naught. Now, the problem here is we want to eventually say that this is less than epsilon, right? And we can't just do that yet. We only know that this numerator is less than delta, but as of yet we don't know anything about the factors in the denominator. So I need to sort of bound 1 over x by something, and I also need to bound 1 over x naught by something. And so that's basically what this proof boils down to, is to find bounds on these terms in this denominator that make this entire thing less than epsilon. Okay, and I'll show you what that's going to look like as soon as I get those bounds. Well, what's the assumption that I have? The assumption I have is that this happens. And if this happens, then certainly it's going to be the case that x lives within some sort of open ball centered at x naught of radius delta. So my x lives in this interval, basically, which is itself a subset of S, right? S is the domain of this function. Well, a subset of its domain, I should say. Okay, great. So what I do know is I know that x is bigger than x naught minus delta, which is the same as saying that 1 over x is less than 1 over x naught minus delta. The only thing here that I have to be careful of is if this numerator equals 0, or if this numerator is less than 0, sorry, denominator is less than 0. If that denominator is less than 0, then certainly 1 over x will be less than 0, but I know that x lives in S, right? And S is equal to 0 to infinity. It's this particular set, so x must be positive. Okay, so it seems I have to sort of restrict my delta. I can't restrict x naught because that's arbitrarily chosen, but I can do something with this delta to sort of make this whole thing agree with the sign of x, or 1 over x. Okay, so keep in mind that x and x naught are both positive, right? Well, somewhere here we have 0. And what we have to do is to make sure that this lower bound can never actually obtain 0 or go to the left of it, sort of loosely speaking. So I need to ensure that x naught minus delta is bigger than 0. And, this will essentially bound this guy. This lower bound will be bounded away from 0. So one way I can do that is to take delta to be a function of x naught, because if you go up here to the gray box, you can see that delta is allowed to depend on x naught. And so one thing I can do is to simply take delta to be at most, well, x naught over 2, for example. I could even have x naught over 4, or x naught over 41. But if I take x naught over 2, then this is nice and simple now, because x naught minus delta is going to be at most, well, this lower bound can be at least, I should say, x naught over 2, right? So essentially now I have that x minus x naught will be less than delta which is less than or equal to x naught over 2. And so that tells me that essentially I have x between 3x naught over 2 and x naught over 2. And in particular, I want to look at this lower bound of x, right? So I can look at this guy here, because if x is at least this, then of course 1 over x will be at most 1 over x naught over 2, which is equal to 2 over x naught, right? Okay, great. So now I have an upper bound on 1 over x, which is what I needed. And it sort of turns out implicitly that I also have a lower bound for x naught, because if you remember here, I needed to ensure that this x naught, 1 over x naught, was at most some value. Well, you remember that I chose x to live in this interval here in this ball, and x naught is of course bigger than x naught over 2, right, since it's a positive number. So that tells me that 1 over x naught is at most 2 over x naught. Great. So it turns out I actually have the bounds that I'm looking for, because now I know 1 over x will be at most, well, one second, let me just make some room here. I'll write it here. Right, we find that 1 over x, the absolute value of 1 over x, which is actually just 1 over x, since x is positive anyways, will be at most 2 over x naught, and also 1 over absolute value of x naught, which is 1 over x naught, is at most 2 over x naught. Okay, great. So now I can put all of this together. Go up here, back to the proof, and I can say, okay, well, this is less than delta over, remember that absolute value of x was less than, well, let's see, what do we write? Right here. So 1 over x less than or equal to 2 over x naught tells me that this entire expression is less than 2 over x naught. I'll write it like this. And then I also have to bound this x naught in the denominator by 2 over x naught. And it looks kind of messy, but just bear with me. This is delta 4 over x naught squared. And now remember that this entire difference has to be less than epsilon, right? So then this guy here, we can set this guy equal to epsilon, and if you do that, then you can solve this for delta. So delta would equal, well, if you solve this, you get epsilon times x naught squared over 4. Okay, great. So now look, it seems that we have found our delta, which is a function of epsilon and x naught, as it should be, or could be. But we also have to keep in mind that the only way to get this conclusion is to make one key assumption. And the key assumption that we made was this right here. In other words, we cannot have this conclusion here without this assumption. Okay, so I have to treat that carefully, and I have to go back up here and let delta sort of reflect that fact. So to reflect that fact, I have to take delta to be the minimum between these two values. And that will give us x naught over 2, comma, x naught squared over 4, epsilon. Well, actually, let me write it like this. Okay, so this is the particular delta that will work here.